can now check transpose. So what is a transpose of a matrix? So a transpose, or to transpose, let's define what to transpose is to do. To transpose a matrix is changing rows to be columns, is changing rows to columns and columns to rows. So this is very simple. In fact, it's a very simple operation that you can do in matrices. So again, if A is given by A, B, C, D, then A, T, that is the transpose. So we have A, then you have a superscript of T is given by so will be given by A, B, C, D. So what has really happened here? So you have the elements A, B, C, D in your matrix, and you have this other matrix here, which is the transpose. You can see that the elements which were arranged horizontally in the transpose, they are arranged vertically. So this is the first row, second row. Now this first row and the second row, they become the first column and the second column. So you invert them so that they become horizontal. So AB vertically, CD vertically, and that is what we call the transpose of a matrix. So that is if A is given by 2, 3, negative 1, 2. Let me use a different number. 4. Then A transpose will be given by, okay, so interchange. This is the row, this is the column. So the first row becomes the first column. So 2, 3 altogether. Then the second row becomes the second column. So negative 1, 4. And the order is given by that. So if this is your matrix A, then your A transpose shall be given by that. That is it. So you can try as many examples as possible to find transpose of matrices. Now, having known how to get the transpose of a matrix, let's check something else called the determinant. So we check the determinant of a 2 by 2 matrix. So if A is given by A, B, C, D, then det of A, also called the determinant of A, det of A also written as, so you can have it written as A, then you have the absolutes. So you have straight lines per se. So the straight lines are given by that, or it can be written as det of A is given by. So we say det of A is given by, you shall multiply the elements in the main diagonal, then subtract the elements in the minor diagonal. As simple as that. So you multiply the elements in the main diagonal, subtract the elements which have been multiplied in the minor diagonal. So the main diagonal is this diagonal, the minor diagonal is this diagonal. So multiply AD, subtract CB. And that is it. So you multiply elements in the main diagonal, subtract the elements in the other diagonal. That gives you the determinant of A. So for example, by A, if A is given by 3, 2, 4, 7, determine det of A. So we are saying the solution, the determinant of A will be given by multiply the elements in the main diagonal. So 7 times 3, which gives us 21, subtract the elements of the other diagonal. 4 times 2 gives me what? Gives me 8. And what is 21 minus 8? So this basically shall give me what? It should give me tired. So that of A, so is 21 minus 8, which shall give me what? Shall give me 13 by the end of the day. So that is it. So the determinant of matrix A is just given by what? Just given by that. And having known this knowledge, we can define something, and we can say NB. A matrix whose determinant, a matrix whose determinant is 0 is called a singular matrix. Singular matrix. So a matrix whose elements or whose determinant is 0 is called a singular matrix. And that is how you determine the determinant of a 2 by 2 matrix. Again, a determinant can only be obtained for a matrix which is a square matrix. Right, together. So it's only applicable to square matrices. Now, having said that, now let's determine the last thing. Then from there, we shall solve simultaneous equations. So now let's get something called inverse of a matrix. So we have something called an inverse of a 2 by 2 matrix. So for a 2 by 2 matrix, the determinant will be given by the inverse. So if A is given by A, B, C, D, then the inverse written as, so it is always written as A, then we have a superscript of -1. So A, then I have a superscript of -1. Then C shall be given by 1 over determinant, should be given by 1 over determinant of A. Okay. Then interchange the elements in the main diagonal. So interchange these elements and these elements. So it shall have our D here, it shall have our A. Then we generally say change the sign of the minor diagonal. Okay. So if it was a positive, they become negative. If it was a negative, it becomes what? Positive. So generally, I can just say change that, because our A, our B, and C were basically positive. Then you can just say that. But in general, what you're saying is just change the sign. Change the sign of the minor diagonal. So interchange the main diagonal, then change the sign of the other diagonal. An example. So an example. A is given by 2, 3, 4, 6. No, let's not choose 6. Let's use 10. Let's use 5. Find A inverse. So anytime you shall see a -1 as a superscript, then that means you're supposed to get the what? You're supposed to get the inverse right together. So therefore, the solution. So the first thing you start by getting is to get the determinant of A. So we know that A inverse is given by 1 over det. Then interchange D. Let's say A, we have -C, -B. So this is a general representation. So the first thing you're supposed to get is get the determinant of the matrix. Sorry about that. So determinant, so det of A will be given by, multiply the main diagonal, which is 5 times 2, gives us 10, subtract 4 times 3, it is 12. So which gives us, our determinant is -2. Okay. Then, so therefore, A inverse shall be given by 1 over determinant. Our determinant is -2. Okay. Then interchange the values in the main diagonal. So these values shall interchange. So 5 shall come here, 2 comes here. We shall have 5 there, we shall have 2 there. Then since these are positives, they become negative. So -4, -3. And that gives you the inverse. As simple as that. So A inverse of a matrix is given by this. 1 over determinant of the matrix is given by 1 over -2. Interchange the elements in the main diagonal have been interchanged. Then we have the other elements which have been negated because basically they were positive. Example 2. Let's check another one. B is given by -2, 3, -1, 0. Okay. So determine B inverse. So I'm determining the inverse of the matrix B. Okay. So therefore, solution again. The solution, I'll find the determinant of B. So det of B shall be given by this times this minus this times this. So 0 times -2 gives us 0 minus -1 times 3 gives me -3. Okay. So you can see what shall change. We have a negative, so it becomes what? Positive. So 0 plus 3, which shall give me what? Shall give me a positive of 3. So always be very careful when it comes to the signs. Right together. When it comes to the sign, kindly be careful. So you have the determinant. So therefore, B inverse shall be given by 1 over determinant. Our determinant is what? 3. Interchange the values in the main diagonal. So we shall have 0 there. And we shall have -2 there. Then change the sign of the minor diagonals. So this one is -1, it becomes +1. So we shall just write 1 without the positive sign. Then this one is 3, so it becomes -3. Therefore, this one shall be the inverse of that particular matrix. Okay. So something else to note when it comes to inverses. NB, you need to note that when you multiply a matrix times its inverse, the answer is always an identity matrix. So you multiply a number times its inverse, the answer is always an identity matrix. Right together. So that is it. So from this point, or we can do an example to verify this. You can have an example to verify this claim that when you multiply a matrix times its inverse, it always gives you the identity matrix. So you can have a very quick example here. And yeah, so a very quick example. So let's say example 3. Prove You are given A as a matrix 2, 3, 4, 1. Suppose are given a matrix A. You prove that A inverse is the same as the identity matrix. So in a 2 by 2, how do you define our identity matrix? It is 1, 0, 0, 1. It is where the main diagonal are all ones, then all the other diagonals are all what? They are all zeros. So therefore, solution. We find the solution, so we can start by finding. So this one is our matrix, so finding A inverse. So we have our A, we can determine our A inverse. So again, determine the determinant of A, which shall be given by 2 times 1, which is 2, minus 4 times 3, which is 12. So 2 minus 12 gives us negative 10. So therefore, A inverse shall be given by 1 over negative 10. Then interchange the values, so we shall have 1, we shall have 2 there. Then shall be negative 4, then shall be negative 3. Yeah, true. So negative 3. So negative and a negative. Now, so I want us to multiply this matrix and this matrix. So A inverse, A and A inverse. So we have your A matrix A, which is given by 2, 3, 4, 1. Then the inverse is this matrix here. So we shall have now, 1 over negative 10, 1, negative 3, negative 4, we have 2. So we can always put this constant on this other end. So we can have 1 over negative 10. Okay. We can always have the constant outside first before multiplying with anything else. Now you can multiply this matrix and this matrix. So let me just first of all rewrite them before we multiply them. 1, negative 3, negative 4, 2. So I've just rewritten that. Now you can see these ones are is a multiplication. So basically we can just multiply them the same way we just multiplied any other matrix. So it is row column. So this one again gives us 1 over negative of 10. 2 times 1 gives me 2. 3 times negative 4 is negative 12. 2 times negative 3, negative 6. 3 times 2 plus 6. 4 times 1 gives me 4. Then 4 times 1 is 4. 4 times negative 1 is negative 4. 4 times negative 3, negative 12. And 1 times 2 gives me 2. Alright. So that just follows the normal operation, normal procedures of multiplying this. So remember, I've kept the constant 1 over negative 10 is outside. Then I'm just multiplying the numbers. Okay. So therefore, again, this one is 1, negative 10. 2 minus 12 gives me negative 10. Negative 6 plus 6, 0. 4 minus 4, 0. Negative 12 plus 2, negative 10. And we said by scalar multiplication, when you multiply a scalar times any other number, times a matrix, it will multiply with each and every number inside this matrix. So this fraction here shall multiply with this number. So what is negative 10 times 1 over 10? That gives me what? It will give me basically 10 over 10. Negative, negative. This times this, 0. This times this, 0. This times this, it is negative 10 over negative 10. Now simplifying further, negative and the negative goes, negative and negative goes, by 10, 1 by 10, 1 by 10, 1 by 10, 1. So 1 over 1 is what? 1. Then you have 0. Then you have 0. Then 1 over 1 again is 1. And this matrix is what we call the identity matrix. So anytime you shall multiply a matrix times its own inverse, then we are saying you shall always have what? You shall always have the identity matrix. And this relationship is very, very important because we're going to apply it when we are going to be solving simultaneous equations. So anytime when we shall be solving simultaneous equations, we shall have this application here because we will not have to calculate since we know that when you multiply a matrix times its inverse, it gives you the identity matrix. And something else to note also, that When you multiply an identity matrix times any matrix A, it gives you the same matrix. Is another very important note, because we will not need to really operate them, because we know, right, together, we already know what we know. So we are saying, if you have an identity matrix multiplied times any other matrix, it gives you the same matrix. Remember, an identity matrix is the same as writing 1, okay? It's the same as writing 1 in matrix form, right, together. It's the same as writing 1. And 1 times anything is the same thing, right, together. So if I take something and I multiply it with 1, I'll get the same thing. So therefore, if I take 1 and multiply with a matrix A, then I'll definitely get what? The same what? The same matrix. So this relation and this relationship here, this and this relationship are very crucial, because they are going to help us solve simultaneous equation. Now from that, let us now jump in to the last part of matrices, and that is solving simultaneous equation. And basically that is a what? That is a 2 by 2 matrix. So again, kindly remember to subscribe, share, and also comment how these lessons are still being helpful to you. So welcome again as we check now how to solve simultaneous equations. That is basically using matrices. So this is the last step, or the last section of what you're going to be covering. Now, so solve the following equation. So we shall have the first one, and we shall check maybe one more. But we're going to be using matrices to solve these particular equations. So we say now these equations shall be solved using what we did last, and that is by inverse method, right, together. So I can check the solution. So there are steps which we are supposed to undertake when you're solving two unknown, that is two equations with two unknowns, that are two simultaneous equations, where you're supposed to get the value of x and y. So we know there are different methods of getting the value of x and the value of y, including elimination and substitution. But now we're going to use inverse method of matrices to solve this particular equation. So now, what are the steps that are supposed to be taken for you to solve this particular equation? So the first thing that you do using matrices, you'll have to rewrite this, the left hand side of this equation, in terms of matrices, and also the right hand side in terms of matrices. So what you'll do, you will extract the constants. So in this case, we have a 2, we have a 4, we have a 3, and our value here is negative what? Negative 1, right, together. So we shall extract those values and write them in terms of a matrix. So there will be 2, 3, 4, negative 1. Then our unknown values, which are x and y, shall be written there. So we shall have xy. Then this other side, we shall have 9 and 11. And all these again, we are saying they shall be written as what? They shall be written as matrices. Now, note something here. When you open up this equation, when you multiply these two matrices, this one is a 2 by 2, this one is a 2 by 1. So first of all, they are compatible in the first place. So the second thing is, when you open this one up, it will just give you these same equations, because you'll have 2 times x, 2x, 3 times y, 3y equals to what? 9. Then 4 times x, 4x, negative 1 times y, negative y equals to 11. Now from this point, now when you have this equation now, you'll have to find the inverse of this matrix here. So we'll have this matrix that we have here, so we can name it. So we can just say let A be our matrix 2, 3, 4, negative 1. So we have to find the inverse of this matrix. So the inverse will be given by, so first of all, we have to find the determinant. So for us to find the inverse, so the determinant of A will be given by, then values in the main diagonal multiplied, subtract the values in the minor diagonal. So negative 1 times 2 gives us negative 2. Then minus 4 times 3, that gives us what? Gives us 12. So negative 2 minus 12, that will give us what? Negative of 14. So that is our determinant. So therefore the inverse, so A inverse will be given by 1 over determinant, which is negative 14. Okay, then interchange the values of the main diagonal. So we shall have -1 and we shall have what? We shall have 2. Then we have then the values here, now since they are positive, so they become negative. So we'll have negative what? -4. We'll have -3. So that is the inverse for this matrix here. Remember, we're dealing with this matrix right together. Then from this point, we shall multiply the inverse, this inverse, on both sides of this equation. So we have this side, the left hand side, and we have the right hand side. So we multiply by the inverse. We can say multiply. So multiply by the inverse both sides. So we multiply by the inverse both sides. So we shall have 1 over -14. Then we have -1, -3, -4. You have 2. Then multiply by, so we start with this side, 2, 4, 3, -1. Then you have your x and you have your y. Then equals to, again, now remember this value starts, okay? So you'll have 1 over -14. Then you have -1, -3, -4 and what? And 2. Then you have 9 and you have what? And you have 11 by the end of the day. So you'll multiply by the inverse both sides, so this side and this side. But now we know one thing that we just did before doing solving this simultaneous equation. When you multiply a value or a matrix times its inverse, when you multiply a matrix times its inverse, it gives you the identity matrix. We saw that A times A inverse gives you the identity matrix. So if this is an inverse of A and this one is A, so we'll have the identity matrix. So we shall have I there, and we have our X and we have Y. Our I basically can be written in full form. Can just write it as 1, 0, 0, 1. Right together. So we have that. Then this other side, again, you can multiply it. So holding this constant. So again, are these two matrices compatible? Yes, because this one is a 2 by 2. You can just write it here, a 2 by 2, and this one is a 2, 1, 2 by 1 column. So there are two. So you can see, first of all, that matrix is compatible by the end of the day. Now remember, if you had started with this one at the right hand side, the left hand side, then this one follows, then the two matrices will not be compatible. So always note that the inverse starts, then you have this particular matrix on the left hand side. Now at this point now you can multiply this, so you can hold 1 over -14 constant, then multiply these two matrices. So again it is row column. So -1 times 9 gives us -9. Then -3 times 11 gives us -30, -33. So we add this and this. What we said, since we are doing an addition, so an addition times subtraction just gives you a negative. So I've just multiplied this and this, this and this. So you have these values. Then you have again -4 times 9 gives us -36. Then plus 2 times 11, which gives us 20, gives us 22 by the end of the day. We shall have -9, -33, -36, then plus 22. Now let's check here. This one is an identity matrix, I. When you multiply an identity matrix times any matrix, it gives you the same matrix. So this side shall narrow down to become x what? Shall narrow down to become x, y. Get it correctly. So we shall have x, then we shall have y on the right hand side, then 1 over -14, then -9, -33. That will give us what? -40 or 42. So -42. Then -36 plus 22. That will give us a negative of what? Negative of 14. Give us -14. Now, so since we have this value, and now note, we said this matrix is a 2 by 2, this one, and this one is a 2 by 1. So these terms here show something we call compatibility. Then the terms that are the values that are outside here shows the resultant matrix. So we know one thing, that our resultant matrix will be a 2 by 1 by the end of the day. So it will be a 2 by 1 matrix. Now let's open this and then we shall verify if indeed it is a 2 by 1. So you have this constant. This constant can multiply now everything. So negative 14 times 42. Negative 40 times 42. That one will give us what? Negative. Negative and a negative gives us what? Positive. Then when you multiply, it gives you what? It gives you 3. Negative 14, negative 14. The negative cancels. Then 14 divided by 14 gives you what? It gives you 1. So now, is this a 2 by 1? Yes, because we have how many rows? 1, 2, and how many column? 1 column. And therefore, the value that you get on this right hand side, left hand side should be the same as what you're getting, because you're using an equal sign at the center. So whatever you have on this side should be the same as whatever you have on the right hand side. So therefore, what will be the value of x? The value of x will be given by, the value of x will be given by 3, because x is the same as the top value here. You have y, a value of y equals to what? A value of y equals to 1. And that is the answer for this particular equation. Now, so we have steps on which you are on how you're supposed to solve. So 1, extract your constant values here. So you'll have extract your constant. So we have 2, 4, 3, and negative 1, and xy. The next step is find the inverse of this matrix. So you find the inverse of the matrix that you let it to be, just give it a name, all right? Just give it a name. So you can say let A to be this matrix, then A inverse shall be gotten from that. So for you to get the inverse, you have to get the determinant, then do the other process where you interchange the values in the main diagonal, then change the sign in the minor diagonal. Then from there, multiply both sides of the equation, this equation here, in terms of matrices, by its inverse, by the inverse of this matrix here. So you multiply with this side, and whatever you do on this side, you do on the other side, because we say if this is an equation, if they're supposed to be the same, then whatever you do on the right hand side, you should do on the left hand side. So, but we know one thing, that an inverse of a matrix times a matrix, it gives you the identity matrix. Okay, so the multiple of these two, we don't have to calculate it. We just write it because we know it will give us an I matrix, which is given by this. Then you have your value of x and y. Then solve this side. You multiply row column, you get this. Then we know again, when you have an identity matrix, multiply by any matrix. Identity matrix, we say, is the same as saying 1, but written now in matrix form. So 1 times anything. So identity matrix times our matrix here just gives us the same matrix, xy. Then this side, you have it simplified in this form. Then when you open this bracket, because this one is a constant, then you have a matrix. This value opens the whole of this matrix. So by the end of the day, you have your value of x, which will be given by 3, and you have the value of y, which will be given by 1. And this is how you solve matrices using the inverse what? The inverse method. So let's see a second example on how to solve functions, or to solve equations using inverse method of matrices. So now we have our second example given by this. So we're supposed to solve using the inverse method. So you can see this one is given in terms of currents. This one I's just to represent currents, but value is just the same thing that we're doing with x and what? X and y. So again, extract your constants. So our constant here is 5, here is 3, here we have 2, here we have 5. Okay. Then our value, our unknown values are I1 and I2. Okay. Then this other side we have 25 and we have 20, we have 29. So therefore again we let A to be this matrix here. So 5, 3, 2, 5. So we need to find its inverse. So first of all, we need to get the what? The determinant of A. So the determinant is given by this times this minus this times this. So we have 5 times 5, which gives us 25, minus 2 times 3, which gives us what? It gives us 6. So 25 times 6, that basically gives us what? It gives us 19. So therefore the inverse, A inverse, will be given by 1 over 19. Then interchange the values. So we have 5 and we have 5, so it will just be the same thing. 5 and we have 5. Then this one is positive, positive, so they change to become what? Negative 2, negative of 3. So we have that. Then the next step, multiply both sides by inverse. Multiply by inverse. Inverse both. Multiply both sides by the what? By the inverse. So again, we're saying it is 1 over 19. Then 5, negative 3, negative 2, 5. Then the matrix itself, we have 5, 3, 2, 5. Then we have I1, I2, then equals to, again 1 over 19. Then we have 5, negative 3, negative 2. Then we have 5. Then we have 25 and what? 25 and 29. So now we know one thing, that from this part, when you have an inverse multiplied by the same matrix, it will give us identity matrix. And identity matrix times any matrix gives me the same matrix. So in short, we're saying this one, but on this left hand side, our values will remain as I1 and I2. We're saying you can always note the values down so that you can verify why this one becomes I1 and I2. So you can just state that A times A inverse gives me the identity matrix, and identity matrix times A just gives me what? It gives me the matrix A. So this side becomes that. Then this side we shall have 1 over 19. Okay. Now, so we multiply these two matrices. So it is row column. Okay. So 5 times 25, that basically gives me 125. True. Then minus this times this gives me. So it is supposed to be positive. It is positive. But now again, this one is negative, this one is positive. So negative 3 times 29, that gives me negative 87. So I think that one will remain negative of 87. Then I shall have negative 2 times 25 gives me negative 50. Then 5 times 29, that should give me 145. So we shall have that. So therefore, I1, I2, we have that equals to 1 over 19 into 125 minus 87. 125, then we subtract 87, gives me 38. Okay. Then you have negative 150, that is 95. Negative 50 times plus 145 will give me 95. So therefore, 19 shall multiply these two numbers. So I1, I2, okay, shall be given by, so 1 over 19 times 38, that gives me 2. Then 95 divided by 19, that gives me 5. So therefore, when this constant opens this one up, so we shall have I1 equals to 2 and I2 equals to 5. So because the top value is the same as the top value here, and the bottom value of the bottom element is just the same. So I1 equals to 2 and I2 equals to 5. And since this because we are using currents, because this one is an electrical, so we shall just shall put the SI units. So it will be 2 amperes and 5 watts and 5 amperes. So this is just a general. So it depends on the variable in which you are working with. But basically, if it is a unit which you know the SI units, then you can always write the value with its measurements, unit of measurements. And that is it for the 2 examples. And you can handle any other simultaneous equation by using inverse method, that is on matrices. And that one marks the end of matrices over 2 by 2 matrix. So again, remember to subscribe, share, and also comment how these lessons are being helpful to you. My name is Mr. Meshak Gige, and see you in the next class.